Hello everybody, and welcome to the 7th online class for MTH218 Multivariable Calculus. Today we're going to look at primarily vector fields and line integrals, which is introducing the idea of vector calculus. So a lot of the words I'll explain it in a second. If you have any questions about assignment 2, you could ask now or at the end, etc., since it's due pretty soon. So this type of stuff I'm doing now is in the exam and your assignment 3, but not assignment 2, in case you're wondering. So today, as I said, I want to talk about the idea of a vector field, the idea of vector calculus, and just starting the concept of vector calculus by looking at line integrals. That's the main thing to do. So before I talk about vector calculus, which is what chapter 3 is about, so the part 3 of the whole subject, I want to go back one step, the idea of vector field. So a vector field is basically a function of n variables, whose result is not just a single number, but is a vector, and in particular is a vector with the same number of components. So pretty much, really, you can be think of as it sends vectors to vectors is one way of thinking about it. Not that we always write it that way. So so that's pretty much what it is. So let's look at 2D examples for the moment. I'll just work, and I'll do a few more, but just the ones we've seen already before mentioning new ones is one vector field we considered is called the gradient vector field. So given any function at all, so any number of variables, so this function of 2 variables, we can work out the gradient vector. So the gradient vector pretty much ends up being a function which goes from 2 variables, so x and y in this case, to produce a vector which has 2 components. So a vector field really is vectors to vectors. That's the real key thing. Another example we've seen is whenever we did the change of variables problems for multiple integrals, which you may have noticed one in assignment 2, for example. So we've really going from a transformation from 2D to 2D, and that can be thought really of as being a vector field. One of the transformations mentioned in the one of the tutorial questions, I didn't actually do it in my online class, had this sort of thing: u equals x squared minus y squared, v equals 2xy, something along those lines, which comes from squaring a complex number. Then you can really bundle them two together as one vector field, if you want to think of it. So these are the 2 components of the vector field. So, and this is illustrative of often how you deal with vector fields, is you can write them as a vector, but often the useful way of doing it is really consider the 2 components separately, and often that's what you really want to deal with. So understand the components or the bits of the vector are a key thing. So that's what a vector field is. I'll give you some more examples in a second of where they might come up in real life, but they're at least ones we've seen so far. So the next part of the subject, so we're starting today, is called vector calculus. That's the last part of the subject. And pretty much vector calculus is really the integration and differentiation of vector fields. That's really what it comes down to. And so that's what we're going to spend the rest of the time on. So we'll start by looking at line integrals. So line integrals, when I very first mentioned them, they don't tend to be vectors at all, but you'll quickly see where they come in. But line integrals are useful in their own right. So where vector calculus is useful in grand scheme of things is looking at how things flow. So you've got a fluid or you've got a force pushing things around, looking at how things flow. And so a line integral in particular is good for looking at how things flow along a curve or across a curve. So line integrals is a bad name. They really should be called curve integrals. But we're stuck with the names for the tradition's sake. You can look at how in a fluid how things rotate, how forces apply, etc. So you can do lots of different things with them. And so we're starting our journey, and there are some really nice high-level results to help you do lots of calculations in vector calculus. I'm not going to do any of them today, so I'm just going to do the the easiest to understand, but sometimes the hardest methods to do today. But we'll start developing some sophisticated theorems which can really help you out. And the idea is to try to use those whenever you can. And we'll look at more of that in time. First, though, I just want to talk a bit more about vector fields. So I just want to look at some common examples of vector fields that we want to consider. So as I said, a vector field, in theory, is given a vector, assign another vector to it. That's what it comes down to. How often they really correspond to is you're given a bit of 2D space or a bit of 3D space, one of the two, and every single point in 2D space, for our first example, you want to assign a vector. That's often the way of thinking about it. I think it's often, and that's a good way of drawing it. So let's suppose you've got a 2D area, so every point has got X and a Y position, Y is height, then the force due to gravity is minus something. And so given the right mass, for example, it can be equal to minus down. So minus 1 pointing down. So this is a force. So the force is a vector, because it has an X and Y component in theory. The X component 0. I want to get a sense of what this vector field looks like. So I will show you how to draw it. There's my thing gone. Here it is. Okay, so this is my vector field, and I want to try to draw what it looks like. So drop my axes here, X, Y. So what I'm doing is I want to consider any points here. So let's just consider a point. So this is given by an X and a Y. So for example, that could be the point 1, 1. And I won't write them all down. Let's just put some labels here. 1, minus 1, minus 1. I'm just going to label the axes. So this point here is a point in 2D space, 1, 1. So this vector field, given an X and Y point, assigns a vector to it. So the way to draw it is to try to draw a little vector on the picture here. So we sub 1 and 1 in. Well, this really can be thought of as just the vector as being nothing in the X direction and minus 1 the Y direction. So this is a really simple one, and it's a constant vector field. So the answer is the same every single place. It doesn't really matter what the X and Y are. But it's a vector in the direction of minus J, in the direction of the minus Y axis. So it's a vector coming down. And it's a length of 1. So if I picked any other point here, any other point, so 1, minus 1, since it's a constant vector field, it's always just arrows pointing down. And you pick any one you want to at all. So that's what it looks like. So this is a vector field, and again, I just picked a simple one to start with. So a useful way of understanding a vector field is us putting vectors in either 2 or 3D space. So I'm doing 2D space because it's much easier to draw, but you could do the same thing in 3D space. Have lots of little arrows sitting in 3D space. You can get Maple to do these things for you. Maybe. No, well. So this is Maple. No, maybe no luck here today. So it isn't coming up very well, so let's just stick with my hand drawing. That's fine. Sorry about that. So this is the idea of so coming back to the general idea is that you can specify the forces in a direct. You can think about forces being anywhere. So that can be an electric field or gravitational field, gravitation, etc. Often instead of talking about the force directly, you talk about the force divided by a unit per mass, which is called a field. So you might want to talk about not the gravitational forces, but the gravitational field it sits in, or magnetic field or electric field. So those are three common examples you see in physics, definitely. So, and so those are common examples. And so some of the high-level theorems that we look at are really some of the key theorems from physics that you may never have seen, but it's good to show you what some of these applications are. We'll come to that later. So forces, so coming off physics, is one important way. That's the instruction I do in Maple directly. We'll come back to later. So another sort of application of vector fields is in terms of flow of fluid, so fluid dynamics, so how things flowing. So given a body of water, so looking at above, so just consider 2D, then given any point x and y, then we can use a vector field to describe how it's flowing at that point in time. So essentially, given it gives an arrow which points in the direction where it's going to flow. And I'll draw the picture, you've got a better sense of what it means there. So what I'm going to do is I'm going to try to draw this one. Okay. So again, like before, we'll put our axes down. X and Y axis. And put some key points down. Let's put a few down for the moment. So, bunches of ones just around the place. So I want to consider, if you drop a leaf, say dropped a leaf in this is a big pond, a big pool of water. If I dropped a leaf just here, which way is it going to go? And that's what this vector tells you, is that if you drop a leaf into the water, it tells you which way it's going to flow. So it's a flow vector. The minus ij notation can be written as brackets instead if you wanted to. They're the same thing in my mind. I often prefer the latter in case I need to make the vector ID quite explicit. But they go hand. They both are important. So let's just consider this point here. 1, 1. So that means x equals 1, y equals 1. So you plug that into this one, you get minus 1, 1. So the x direction it's pointing in the negative x direction, so going that way, and in the positive y direction, so up that way. So it ends up being a diagonal that direction. And it's good to think about the length is, by the way. So this is the vector. I'll write up the top here just to my working sake. That's minus 1, 1. The length is the square of the first one, 1, plus the square of the second one, 1, square rooted, so the length is root 2. So I'll try to draw that. So it's good to have the direction, but also the length of it to be meaningful on these pictures. So I'd say if you dropped a leaf in, would start to flow in that direction. Yeah, as it goes on, it wouldn't stay that direction; it would change again. But we'll see. So let's pick some other ones. So let's pick 1, 0. So x equals 1, y equals 0. So if you plug that in, x equals 1, y equals 0. So you get the vector 0, 1. That means there's no x component and it's sticking up 1. And the length, if you work the length for it, would be 0 plus 1 square root gives you 1. So it's actually shorter. So it's shorter than the one above it. So I'm just going to try to indicate that. You can plug another point. So you plug in 1, so 0, 1, which is this one up here. The x is nothing and y is minus 1. So therefore that'd be a vector pointing in the x direction minus 1 and 0 in the y direction. And again, the length is 1. And you can keep going. So you can keep going other points. So you can keep drawing vectors all over the place. If you did the origin, you get nothing. So if you dropped a leaf right bang in the middle of the origin, it wouldn't move, seemingly. Well, it wouldn't move x in the x and y direction, at least. It would probably, that's all. So that's a few points. You could sub other ones in too. So you could pick on sub in 2 and see what happens. And you can see, I'm just drawing a few more vectors. So you could keep subbing in, just some random points, really. How would you describe what that looks like? I mean, that's just only a few arrows. I haven't done them exhaustively. Can you, from that, work out how it is flowing in general? How would you describe, if you saw that in a river or a lake, how would you think about describing it? So someone's going to have a go. Thank you. So I'm asking these things just to think about, just trying to think, well, they're physical ideas, just try to get a sense of, well, what does it really mean? Because we're going to do lots of calculations, but it's good to see where it fits in. Okay, so someone says counterclockwise vortex. That sounds fancy. So circular flow. So you're going to flow in a circle, that's right. A few things to comment on, so I like both those descriptions, is just a few stuff. So let's just do a position vector for the moment. So you picked any vector at all. Here's one here. This is the position vector. This is the vector from the origin up to a certain position. That would be given by x, y. So a few things to notice, and for short, I'll write that with an X with a little squiggle underneath it. Or if I was typing up, like in the notes, I'll make it a bold X. That's my shorthand notation. So if I did X dotted with the force, so if I got the force dotted with this position vector, that's just a way of saying, a shorthand way of saying x, y, dot product with minus y, x. So I take the dot product of those things, I get x minus y plus x times by y, and you see that's equal to 0. So if you take the position vector and this force, or sorry, it's flow, isn't it? So if you talk dot product with the flow, you're getting 0. So that tells you that it's always flowing perpendicular to the position vector, which is, again, really suggesting that it's a circle. So it's really moving in circle motions, which is what both people were referring to. It's a key thing. Other thing to notice is the length. So if you did the magnitude, so the magnitude of this flow, so which corresponds to how fast it's flowing, really, would be minus y squared plus x squared square rooted, which is just another way of saying that's the length of this position vector. So how fast it's flowing effectively really is determined by how far away it is from the origin. So they're flowing in circles. So if you dropped a leaf in anywhere, so here for example, it'd end up flowing in a circle. So it's not it's not a whirlpool, as in it's not sucking towards the middle, not this one at least. It's just flowing around in circles, so it just always keeps spinning round and round. And how fast it's spinning is determined by how far away it is from the origin. That's how this one particularly works. And it's not moving at all. So if you happen to drop a leaf right bang in the middle there, it would actually spin around and it would spin on a circle. And so it would just spin around the middle point. That's what it would look like in practice. So it's good to think about what it is, because later on we'll start doing some differentiation of vector fields, and they are useful for diagnosing things like if stuff is spinning. So we'll do it. You can do a certain derivative of these things which determine how much it spins, but we'll do other ones like seeing how much it flows in and out at points in time. So we'll come back to this one. So this one has no net in or exit flow, but certainly has lots of rotation to it. So there's some things that are useful to think about. So as I said, really it's just body of water, things flying, and you can make it 3D as well if you wanted to. So you can have an I, J, and a K component, so 3 different, and X, Y, Z. They're just harder to draw, and so I'm going to leave those alone just for the moment. Okay, so that's vector fields. If you want to try to get, let's see if I can try to get. So this is Maple's way of doing it. So the command is more usefully written in the slides there. Let's make it a little bit bigger. So just doing, it's with plots. It's called a field plot. You name the vector field, and then just a region of X and Y you want to do it in. And let's see if I can make it bigger. Oh, well, sort of. I'm not sure how well you can see that. The arrow's getting look pretty small. But as you can see, what Maple does is they've drawn arrows, everything, and you can really see that spiral, that circle effect. The things going around in circles. And you can change the function slightly to make it into an actual real spiral. But you can see I got a reasonable answer by just subbing in a few random points, in this case at least. Okay. So what I want to do is not just do vector fields, I want to do some things with them. So I want to consider a few different types of both integration and differentiation you can do with the vector fields. So the first integration we want to do is called a line integral. And as I sort of said into my preamble they really should be called curve integrals. They're really just integrating along a curve. And so just like we've seen with generalizing integration from one variable to two variables on different regions, well, we could have just stuck with one variable, but just made it into a curve rather than a straight line. That's what we're considering here. And so at first glance, you go, well, where are the vectors? And the vector in general is the tangent vector, or the normal vector at any point in time on the curve, is often where the vectors come from implicitly, but we'll see them in a second. So there are two types, so a few things. I'm going to mention just two. I'm going to consider curves just in 2 dimensions today to keep it simple, but the same ideas work in higher dimensions, so 2, 3, etc. In physical quantities, 2 and 3 are the main ones you want to consider. So there are two types of line integrals: scalar line integrals and vector line integrals. The scalar ones, the only real method to do them is what I'm going to mention today. For vector line integrals, there are some really powerful theorems that you can apply to help make these calculations easier to do. The theorems themselves are a bit more complicated to understand, perhaps, but they're really useful. I won't mention them today. I'll start mentioning some of them next week. But they are there. It's just worthwhile mentioning that. So let's look at two different types. So the first one's called a scalar line integral. It's good just to... so what they look like is an integral along a curve in space of some sort of function of many variables, and you write ds, and the little s here corresponds to a small amount of length of curve. So you did length of curves in, say, Maths 101. The same idea, really. It really is just an extension of working at length of the curve. And the calculations, you'll notice, are really similar to what you might have done in Maths 101. So what it corresponds to, some applications of this thing is, if you want to work out the length of a curve, then you'll just integrate 1 ds. So you make this function here, the rho xy. If you make that into equals 1, that will give you the length of a curve. So that's one useful application for it. And again, you've actually done that. Those calculations you've done in Maths 101, for example. If you've got a piece of wire or whatever it might be, and you know the density of the wire at any point in time, and this would be the density of it, then integrating that little bit of density along the whole way would give you the total mass. So that's what it is. So really it is adding up a function, or totaling a function along some sort of curve. That's what it corresponds to. And so I think a good example to keep in your mind, if you want to go, what am I doing again? What does this correspond to? Is thinking of the mass, total mass along a curve where that's the density. That's my go-to application, I think, of this one to visualize in my mind. Now that's the application, but how do you work them out? Well, the way to work it out really is just by substitution. So integration by substitution, really. And that is, if you've got a curve, you have to work out a parameterization for the curve in terms of one parameter. It's a straight line. It's a curve after all. So let's make x equals xt, y equals yt, and again, you need to know that use the context to work out what the parameterization is. And then just sub in from there. Yeah, that makes it sound simple, but in particular, the ds bit here is equal to the length of the tangent vector, is the fancy way of saying it, or it corresponds to the square root of the sum of the squares of each of the different derivatives. So if you've got all these different, values, x, y, z, etc., if you take the derivative of every single one of them, take the square of all of those things, and take the sum them all up, take the square root, that is the length of the tangent vector, and the ds is just that length dt. That's what it corresponds to. So in 2D, that's a simple formula, which is just easy to remember it as it is. And you may remember that particular formula from S101, for example. And if you do it in 3D, it's the same sort of formula, which was not mentioned in Maths 101, admittedly. But it's a similar idea, very similar concept. And so to work it out, just plug in the functions, replace all the x and y's by t's, and just replace the ds by this formula. So I'll show an example to make it a bit more concrete in a second. Looks like someone almost had a question there. Okay, so okay. So here's an example. So I've got a wire. So I've got a y in the shape of a circle. So this is my curve essentially. So I've got a curve here. So it's a y in the shape of a circle. The density is given by y squared kilograms per meter. So if you've got a little bit of section of it, then the density of this, that's the density, is y squared kilograms per meter. What I want to do is work out the mass. So the way I think about this is, the way of working out the mass is I'm going to split it up into lots of little bits. And each little bit, I'm going to work out the mass for the little bit, so a small amount of the mass, and I'm going to add them all up along the whole way. And since the whole thing's sitting on a curve, I'm going to integrate along the whole curve. That's how I think about integration. It's just breaking it up into small bits, adding them all up. So what you really have to do is work out, well, what's a small amount of mass then? Well, since I know what the density per meter is, I just do the density and multiply the density by, well, just the length it is. And a small amount of length is a small amount of arc length, or ds for short. So therefore that gets the formula. So mass for this sort of thing is the integral of the density times ds. And that's just deriving the formula, so to speak, really. So how do you work that out? So that's going to be y squared ds in this context. So I might as well write that down. So that's really what our question corresponds down to. So if you go to tutorial 7, which you're going to practice these things, most of the questions will look like that sort of form. So you don't have to work it out. And really what it comes down to, as I said, is just knowing a parameterization for the curve and then subbing in. Now, one more thing while I remember it. Because C is a closed curve, so the two endpoints meet up, a common notation is to put a little circle through the integral sign, like that. And that is basically saying you're integrating around a closed curve. Yeah, it's not compulsory, but you might see it from time to time, so just mentioning it so you've seen it. So how do you work it out? Parameterize the curve. So I've got a circle. Circle of radius 1. Does anyone know what a good parameterization for that circle is? It's just testing a memory. So we actually have covered it in this subject all the way back at the very beginning of the subject. But can anyone remember what's a good parameterization for a circle of radius 1? So I need to say x is equal to something, y equals equal to something for some sort of parameter. Anyone remember? Yeah, people having a go. Good. I'll let people have type in an answer. Take some time to type up stuff. I'm keeping talking just so people realise that the silence is not a break or something like that. It's okay. So you're going to work it out. Once we work out the parameterization, which is I'm waiting for it to come up and people think about it. Yep. So x equals, in general, r cos theta, but the radius is just 1, and y equals r sine theta. Again, there's 1. So cos theta, sine theta. So we've seen that in polar coordinates, for example. So once we know what a good parameterization is, we need to know the limits. What are good limits for theta? You've got choices here. It's got to be around the full circle, right? So I would like to make it minus pi to pi. That would go all the way around. You could go from 0 to 2 pi. That would also work. But I like this one for it. I'll show you why in a second. If you do x, then now in order to plug into the formulas, we need to know the derivatives. So x is cos theta, so you need to take the derivative of this one. So derivative of cos is minus sine, and the derivative of y is positive cos. And so the key thing we need to know is work out what the small amount of length is. So small amount of length is given by the square root of getting all these different derivatives, so all of them, squaring each of them and adding them all up. So just add them all up. So I've only got 2 here, but if I had a third variable, a z as well, I'd have to do a plus z dash squared as well, and take the square root, and then do d of the parameter, in this case theta. So really just have to work out what this square root thing is. So x dash would be minus sine squared, so the signs disappear, so it's just the minus sign disappears. Plus y dash, which would be cos squared. D theta. So what is sine squared plus cos squared equal to? You remember? Yep, lots of people. So it's 1, so that ends up just reducing down to d theta, which is pretty nice. So for circles at least, we have something pretty nice here. So so what this happens to be is that this parameterization for a circle is parameterized by arc length, by the length of the arc, which is why it's so nice. So circles are one example, which you commonly see that. You can do it for straight lines too. Other curves, it's much harder to parameterize by arc length, but it's useful sometimes. So therefore, putting all together, we want to integrate along the curve of y squared ds. So the trick really is just to replace it by the parameterization. So replace y squared by the parameterized value, which is sine theta. So give you sine squared theta, and the ds replaced by this expression, which ends up being just theta in this case. And theta goes from, as I said, minus pi to pi. Now, because sine squared is an even function, so when you square plus or minus, and when you square sine or cos, you get an even function. I can write that as double from 0 to pi of sine squared. So I'll put the 2 in the middle actually. So it's using even functions. Now you don't have to do that, you get the answer out anyhow. Now, I don't remember how much you remember. But so the integrate cos or sine squared really is just about using the doubling result. So sine squared is 1 minus cos 2 theta on 2. Cos squared will be 1 plus cos 2 theta on 2 is how I remember it. So I'm just using a standard result, which you would have covered in Maths 102, for example. I hope you did. So that's a common way of integrating sine squared. And so I'm just reading integrating 1. So integrating 1 is theta. Integrating cos theta would be sine. And then using reverse chain rule, I have to divide by the derivative of the inside function, divide by 2. So subbing in 0 and pi. So zeroing 0 and pi in the first term gives you pi. So having pi and 0 into sine, so sine of 2 pi and sine of 0 both give you 0, so they give you nothing at all. So the final answer is just pi. So therefore the total mass of this particular wire under that parameter thing would be pi, whatever units there, so kilograms were the units I specified, so pi kilograms would be the weight of this particular wire. So I just want to show, just refreshing, to do a scalar line integral like this one, which always have the DS's, really just do integration by substitution. And the key thing really is to remember these results. Remember how to write ds in terms of that parameter. That's really what it comes down to. Now on the formula sheet, you have those written down. So if you like, these things will be written down in vectors really nicely. It's just the length. So that's how you write it for short. So it's the length of the tangent vector. But I think it's often easier just to know the full explicit formula rather than vectors are a really neat way of writing it down. You see that a lot in vector calculus, but sometimes the explicit formula is probably more useful because that's what you're going to have to do. That's called a scalar line integral. So the other type is called a vector line integral. And so we have, there's three common sort of forms, well, so there's a few different forms you can see. So simple forms is you're integrating along a curve, so it's the same idea, so still integrating along a curve. But instead of integrating it with respect to the arc length, you're integrating with respect to some other variable. So it's integrating along a curve of a function, but it's required to dx or dy. So you're adding up the amount of changes of x along the curve. If that's what this one is, that's the total amount of change of x along the curve. This one is the total amount of change of y along the curve. You can even put them together. So a common way of doing it is sort of notation at the bottom. That's integrating p dx plus q dy. That's how you write notationally. What that really means is just doing them both separately. So just do the integral with respect to x plus the integral with respect to y. So these are all three different forms of writing it. You can also integrate along curves into 3D space as well. Then you can have a dz available. So these are called vector line integrals. And you're thinking, why vector line integrals? If you write it, say capital F as a vector field with the components p and q, so this is our vector field here, then for short, I would write this as the integral of the vector field dot producted with dx. And if I'm writing this down, I'll show you how to write it down manually. So by hand would be f vector dot product with x dx vector, and x vector is just a shorthand for all the different variables we have. So x and y in this case, that's 2D. In 3D, I write it as x, y, z. Now, this comes from physics, and so because x with a little squiggle underneath it, sometimes can be confusing for the variables themselves, like that can be really confusing. Sometimes we would write down r with a little squiggle underneath it instead. So that's alternative notation. So therefore, the integral of f dot dr is a common way of writing this down for short. And that notation is handy. So all these types really boil down to cases of this, what it comes down to. As I've said a few times, there are actually some really nice results to solve these things quite directly. So in the special cases, you can write, the answer is very simple to get, but the method's a bit more advanced. So we'll do them later. So I just want to do the simple method. So simple meaning easy to understand. It can be quite time consuming, and really the method that I'm proposing is just integration by substitution. That's all it really is. So it's still integrating along a curve. So you just parameterize the curve somehow or other, and then really just plug in, replace x by its parameters. The key thing is when you write, say, a dx or dy or dz, etc., just replace it by its derivative times by the parameter. That's all it corresponds to, which is what you do. That's how you do integration by substitution normally, for that matter. That's all that's it. So this is easier than the DS integrals because it's much easier to write down. Okay. So I'll do an example, and in the process of the example, I'll mention some applications for it all. Now I can see my didn't work out. So let's make the example a bit more informative. This is so I've got two electric plates. This is a wire. So this is a circuit, one with a positive end, one with a negative end on it. It's two metal plates. And so if you got two charged plates like this, then you get then you get an electric field going in this direction here. So from one plate to another. Or putting it another way, that if you put a particle, so a little proton in the middle of it here, for example, it would move towards the. You've got to put an electron here, so I'll put in electrons. Sorry, I've got to get my units right. So the standard way of writing this down in physics, it would be in terms of the proton. So if you chuck a proton in the middle of the field, it will flow towards the negative end of the plate. If you put an electron, it's the other direction, complete opposite. So this is a nice constant electrical field. So the force on any charged particle in the middle of this thing would always be the same. So let's suppose that what we're doing is we've got in our middle of our field here. So that's our standard axis here. That's x, y. So in our electric field, we've got a wire in the shape of a parabola. So I've got a little wire here. Now, charged particles like electrons, for example, can flow along this wire. So if you moved an object, or an object was moved by so this is all force. So if you chucked a proton bang in the middle of it here, then what will happen, this force will actually push it along the wire. How much energy would it gain? How much energy would this particle gain as it goes along? So that sort of increase in energy is called the work the force does on the particle. So work. So the work done on the particle. And it's really just an energy, just how much energy it gains. And if it's a particle in space, so if you were just one single particle and you just happen to restrict it to the circuit somehow or other, then it would be that increase in energy would go to kinetic energy. So how much faster it would get, for example, along the wire, gives you different sort of other things. So how you work out the force? So the work done. So work done ends up equaling the amount of the force dot product with dx. That's the formula for work. So it's the direction of the force. So the dot product really is just saying that the direction of the force in the direction of the curve. That's what it's doing. And then, so I mean, you can work it out as being it's f dot producted with the tangent vector ds. It ends up being what the whole thing simplifies to. So you can actually resolve it to a scalar integral. But how we work it out in practice is not that way. So it really just working out what the component of the force is along the curve and adding it up. And an f times by the distance it moves is just the amount of energy it gains at any instant. So that's the simple formula for it. So in this case, we just have to think, that's a really shorthand for it. Let's what it corresponds in this case. So f here is really can be thought of as just a vector with two components, both being 1, 1, 1. So it's really just 1, 1 dot product with the differential, so which is dx, comma dy. So dx tilde is just shorthand for dx dy, so just a vector of differentials. If you take that dot product, you're getting 1 times by dx plus 1 times dy along a curve. So this integral here would give you the total amount of work that the force here does on a particle as it moves along this particular wire. This electrical force does on the wire, or how much energy it's going to gain. That's sort of the thing we have in our mind. So you just have to work it out. And I said the way to work these things out, so I've got it from an application of work that a force does on a thing, an object, is my application of these vector line integrals. Often, as you'll see, the questions you'll get end up being ruled just like this last form, what's in the box here. The way to do these things is really just to parameterize the curve. So we have a curve, just parameterize it. In this case, it was told to, so we're at the top here. So it's a parameter, it's a parabola, so it's x equals t, y equals t squared, and t is between 0 and 2. So this is given in the question. That's a parameterization. So once you parameterize it, we just need to work out the derivative, because we're really doing integration by substitution. So derivative of t is 1, derivative of y is 2t. And then dx then is equal to the derivative times by dt, which is just, well, derivative of x is just 1, so it just ends up being dt. And dy, again, simple, straightforward substitution stuff is y dash dt, whoops, y dash even dt, so that would give you 2t dt. So now we have all this information, we just plug it in really. So now I've got the integral along from 0 to 2, we're changing everything to t's, of 1 dx, which would be 1 times dt, plus 1 times 2t dt, so plus 2t dt. Now if instead of 1s you had an x or a y there, you just plug in, if you see anytime you x, you just put a t, anytime you see y, you just put t squared, just sub in. Make it a normal integral, just put all lots of dt's, so the integral of 1 plus 2t, like that. And then we plug in then we just integrate it normally. So integral of 1 would be t, integral of 2t would be t squared. Plugging in from 0 to 2, so sub in 2, you're getting 2 and plus 4, which is 6, sub in 0, you get nothing. So the total amount of energy gain, or the total amount of work the force would do on a positive particle as it moves along this wire, would be 6 newtons. So give a standard units of force, 6 newtons. So a few things. One is if you ever to do the default option. So if you can't think of anything, if all the high-level theorems don't work, which is normally the best way of doing, any vector line integral can always be done by integration by substitution. And that really is just to work out a parameterization, take derivatives, replace the dx to y appropriately, plug in, and it just reduces to an integral of one variable. Just go for it. Now I picked a really nice function vector field here. A more complicated one meant that integration could be really hard if you're not careful. And so looking at some of the high-level theorems to simplify them would be a good thing if possible. But this is always a good fallback option. So this is, I think, this is a fallback way of trying to do these sort of problems. So in terms of what applications would you get for it, this is my better picture of what we're doing. So this is my vector field, and you can see that's the little y we've got there. And a few things is a scalar line integral. When you're parameterizing a curve, it doesn't matter. So with that circle, we parameterize it so it's anti-clockwise. We could have parameterized it so it was clockwise, and we would have got the same answer. The direction you go the curve doesn't matter for a scalar line integral. So scalars have no direction, but for vector line integrals, the direction makes a point. So we went from the bottom here, 0, all up to x equals 2. If we'd moved the particle in the opposite direction, it would have lost energy rather than gain it. And so if you did the line integral in the opposite direction, you wouldn't get you would get minus 6 rather than positive 6. So direction is important for a vector line integral. I'll say that again. Direction is important for a vector line integral, but not a scalar one. So that's one of the big differences between the two. So that's the sort of picture. So just applications, where do you see vector line integrals? So we'll do them in their own, we'll just do some calculations, but where you see them naturally is by work done by a force, like that last example. They also come up in fluids flow, which is the other key example I made. And so if you know what the flow direction of if you know that a fluid is given by a certain vector field, the flow along the curve is just f dot dx. You can also work at flow across a curve too. Maybe a picture would be helpful. So we had a vector field going in circles before. What you could do is you could have a line or something like that, and you might want to consider how much water is flowing across this curve, which means perpendicular to it. So you can work out how much it's flowing across it at any point in time, which would be important for if you're doing a dam or working out how much water is the total amount of volume of water flowing through a certain region or straight line or whatever it might be. The total flow across the curve can also be done via a vector line integral. So it's something similar. So instead of integral of say p dx q dy, it's just making it a normal rather than tangent. So it's integral of p dy minus q dx, for example. I got a plus or minus sign at the front, if you notice. The direction is important. So it depends if you're going down or up, which direction you're considering that you want to concern, and that will give you the different signs. So what becomes important for lots of these vector calculus ideas is having a key direction in mind, or putting it another way, you need to know the orientation of the objects you can consider. So for our curve, we did in that last example, we had a direction or an orientation of the curve. It goes from one to another. That's called the orientation of it. Also, if you want to have so that's important to understand. And so if you want to consider the flow across a curve, well, which way is it flowing? Is it to the left or to the right of that direction? Now, the standard approach is outward flow. So often we would consider a closed region and we're trying to consider it flowing outwards. But yes, so the positive sign is the default option, as I've written in here. So that's some application. So that's the main things I wanted to cover today. If you've got any questions about that, fire away. But so what you need to do is top priority finish assignment 2 because it's due tomorrow. This stuff is looking at tutorial 7, so questions from tutorial 7. So I want you to have a go at those. The questions aren't really along the lines of the applications, but I mentioned just to give a sense for how it all works. And they really are just the integrals themselves. So here's some integrals along curves, given a parameterization of the curve. Just do integration by substitution for all of them, whenever you can. Some of them with the DS's, you have to remember that formula. Otherwise, just do it directly. And you need to be able to do it for both 2 and 3D. Both of them are important. But it's good that I think these ones just help you give a sense for what are we trying to work out here, and give a sense of the differences. There is a relationship between all of these things. So the total amount of flow along the curve is a flow dot product with the tangent vector ds, and it's the let me get this right. So the unit tangent vector. So it's basically what this is saying is it's working the total amount of the flow in the direction of the tangent, adding it up. That's a one way of the formula. Now, if you worked all those things out, it ended up simplifying down something much easier. You can also work the total. So the other one I wrote down was P dy minus q dx. That's equal to the amount of the flow dot product with the normal ds. And again, unit normal. So depending which direction, if you wanted to go it along the curve as tangent or across the curve for normal. So you can actually, all these vector ones can be resolved down to scalar ones if you wanted to, but in practice, that's not really the way. That's not a helpful way of working it out. Because if you waded through all of that, you go, hold on a sec, it just simplifies down to something nicer. Why didn't I do that in the first place? But there is connections between the two. But so a key things to notice is you've got lots of components, which are different in front of all the dx dy bits for a vector one. For a scalar, you've just got the ds, really. But in practice, at first glance, they don't seem very different to how to work out. Where you really will notice difference is for vector line ones, you get lots of extra really nice theorems, but for not, you won't see them for scalars. So I hope that's helpful as an introduction. I was trying to give you a sense of what it all means primarily, and a little bit of showing how to calculate it. So I hope that is helpful. If you've got any questions, fire away. But otherwise, I'll see you next week to look at some of the more high-level ways of trying to tackle this vector calculus and continuing our understanding of what it all means, etc. So thanks for your time.